All right. Hello. Howdy, astronomers. Welcome to the Colloquium. It's my great pleasure today to introduce Kevin France, he's giving this talk in part of his promotion to full professor. So Kevin earned a BA in physics and astrophysics at Boston University some years ago. He then earned a PhD at Johns Hopkins, and then after a brief stint in Toronto, has been here for much of his career since 2007 in various roles. So currently Kevin leads the Colorado Ultraviolet Spectroscopy Program, CUSP, they're always on the cusp of making exciting new discoveries, as well as the rocket group here that is just constantly launching a flurry of new instruments up to the edge of space. So scientifically, Kevin is an expert in stars and planets and disks, but I think he's particularly known for the beautiful instruments that he builds that help us see the universe with new eyes. And he has, if you read through his CV, you will see an extensive list of acronyms of projects that he has been responsible for, that he has helped lead, everything from CUTE, a tiny little telescope, up to the Habitable Worlds Observatory, the next great telescope coming in the decades ahead. And so being unable to do honor to all of the amazing missions that you've built, Kevin, I'm just going to take the inspiration from your acronyms, which are always quite good, and horribly summarize your career as Kevin explores very ingenious new frontiers of research in astrophysics with novel and clever experiments, which we'll hear about today. Kevin France.
Thank you, Zach. I appreciate it. Yes, I probably spend more time than I should. Thank you. I'm really grateful to be here. When I moved to Colorado in 2007, I was not imagining being here. So I'm grateful to have this opportunity to talk to you today. So you've seen a lot of exoplanet talks. And so when I was thinking about how to talk about the search for life and new missions, I wanted to kind of bring it home to Colorado. And so I started working on this extended analogy talk where we would talk about hiking as an analogy for the search for life. And I told this to my wife, and she said, "That's a very interesting idea, but you're going up for promotion, right?" And I said, "Yeah." She said, "Maybe don't." So I really backed off from that. But I couldn't, I have been thinking about exploration and the connection between science and exploration recently. So I'm going to just for a minute, I'm going to do it. And then I'm going to hide an actual science talk in there. So this is going to be a talk about the search for habitable planets. And we're going to start off here at home on a sort of easy to walk trail and a lush outpost that we know. Right? This is the analog for Earth here. Ultimately, we're looking to climb a summit to find habitable planets beyond our solar system. We want to understand, we don't really know what this looks like, but we want to understand, are they out there? How common are they, and what are they like? This is going to be hard. Along the way, we're going to be going through new environments. It'll look different than what we are experiencing here at Earth, and probably we're going to get to a few places, and I'll tell you about at least one of them today, where we thought we might have had a glimpse of the summit, but it turned out to be a false summit, and we had to keep walking and walk further up the hill. But no matter what, it's going to require us to take on certain technical challenges that are beyond what we are used to, which means that we're probably going to need to buy some cool new gear. All right, so you can tell me later that, yes, Kevin, your wife was correct. You should not have done that. But it's better than it was. All right, so how did we get here? So I want to show this movie that highlights the exoplanet discovery space as a function of time. So this is a movie that was produced by the NASA's Exoplanet Science Center to celebrate the 5,000th confirmed exoplanet. So you're going to see these things pop up. This is primarily in the early days radial velocity observations and a few transits. In 2009, the Kepler Space Telescope was launched. And then a few years after that, you're going to see the Kepler field, which is right about here, explode. And this is where we've gotten the majority of our planets from now, which is transit observations. There you go. And then if you remember what happened to Kepler, its reaction wheels failed, and it could only observe in certain parts of the sky. So you're going to see the places where Kepler could point after that fill in here. And this is going to take us to 5,000 confirmed planets by 2022. The number today is a little over 6,000, but they didn't remake the movie. And so with all of these planets now, a big focus is what's the next step? How do we go from finding all these planets, right, which has totally rewritten our textbooks, to finding the planets that look like Earth? And so this was really highlighted in the decadal survey. I'm not going to really talk through all this, but the decadal survey's first theme was called Worlds and Suns in Context. And it emphasized studying exoplanets and stars. I think that's important, with the goal of finding potentially habitable analogs to our own. It did this in sort of a little bit more detail by having these specific focus areas, and the pathways to habitable worlds was the focus area. And again, similar, the goal is trying to discover worlds that could resemble Earth. So this is the recommendation that gave rise to the Habitable Worlds Observatory that we'll talk about at the very end of the talk. But this same question is driving how we use our current great observatories. So there was a community working group I was a part of in 2023 and 2024, which was basically asked the question, we're at this special time where Hubble and James Webb are working together. How do we optimize this for exoplanet science? And so there was a group of us that worked for about 18 months to write a paper that was actually led by former CU alum Seth Redfield. And it said that we should really go after rocky planets, right, with the idea of finding which of these planets might host habitable atmospheres, or any atmospheres, which I'll talk about in a minute. And it said, understand the prevalence and diversity of atmospheres on rocky M-dwarf worlds, right, these are terrestrial planets, and understand exoplanets in the context of their stellar environments. So this theme of stars and planets and how they get along, and not just finding the planets, but also understanding the things that drive their atmospheres and their evolution is a big topic. OK, so what are we looking for? So I'm going to show this plot that you've probably all seen, right? This shows the habitable zone as a function of stellar mass. And if we put spectral types on there, you know that this is not to scale, but the habitable zone distance is proportional to the stellar luminosity. So if you go around a cool M star, the habitable zone moves in. If you go to a more luminous star, the habitable zone moves out. And Astro 2020 kind of had one of the questions that paraphrased that pathways area was, what's the range of potentially habitable environments around different types of stars? So today, we're studying M-dwarfs with JWST. Zach gave a very nice colloquium a few weeks ago talking about this. I'll mention it again. And then in the future, we're going to be looking for true Sun-Earth analogs, and we're going to be doing this with future missions like the Habitable Worlds Observatory. The thing all of these star-planet systems have in common is that they need to live in the context of their host star. So with that in mind, this is the outline, what I'm really going to talk about today. I'm going to first introduce the differences, different type of exoplanet host stars. Surprise, they're not just the sun. We're going to talk about the influences of those host stars. What do we need to do to understand the key influences for photochemistry, for atmospheric retention? And then looking to the future, how are we executing the search for a true Earth 2.0? One thing that I wanted to emphasize right off the bat is that this talk is the result of probably 6 people. So I just wanted to highlight some of the people who have come through my group. These are the students that I've had since I've been here. Highlight our research scientists. I want to sort of give a special call out to Brian Fleming, who's been my partner in crime for pretty much all of the instrument work that we've done here in the past 10 years. There are more students. In fact, we just did Nico's paperwork for his PhD this morning. Some students who are my current students who haven't graduated yet, and some students who are not technically my students, but are engaged in a lot of the day-to-day work that we do. And there are more. I could go on and on. One thing that, the people in blue here are people who have contributed to the things that you'll see in the talk today. What I'm not going to do is put individual pictures in there because they would A, overwhelm the slides, and B, convey the correct impression is that I don't actually do very much of the work myself. OK. So let's talk about the stars and what their influences are on orbiting planets. So this is just a cartoon version that shows different aspects of the star emit different types of radiation and where they're absorbed in a rocky planet's atmosphere. And we're going to highlight two aspects of this. Before we highlight those, we're going to talk about the difference of the stars. So I'm going to talk a lot about the difference between red dwarfs and solar-type stars, just to orient us so we're all talking about the same things. We're going to be talking mostly about high-energy radiation, because this is what drives atmospheric loss and photochemistry. These are some wavelengths, just so when I say them without defining the wavelength, we know the same thing. X-rays are also sometimes important, and on this plot they fall slightly off the edge because it's not a log plot. And the first thing that we're going to talk about is photochemistry. And so the atmospheric photochemistry is largely driven by the near UV and the far UV radiation from the star. To do this, we've been making use of the Hubble Space Telescope for a really long time now. And so a lot of the advances in our understanding of exoplanet host stars have come out of a couple of dedicated large projects. The largest of those is the MUSCLES project, which we've led here at CU for almost 15 years now, covering a whole bunch of HST cycles where we also get X-ray and ground-based observations. I'm not going to talk about the data products today, but just to say that a lot of the results that you're going to see come out of this MUSCLES team that has been working here, students and research scientists, people who are here and who are no longer here. Rather remarkably, I looked up some publication statistics as I was putting this together, and I have been on over 50 publications that are either describing the papers or using these data, with over 3,500 citations to those works. And for somebody who kind of started life as a lab rat and who only was really good at putting instruments together and calibrating them, I find this number kind of amazing. So it just goes to show that you can change horses midstream at some point and do things you didn't think you could do. All right, so let me talk a little bit about one particular result on the photochemistry side, and then we'll shift gears a little bit. So one of the things that drives the photochemistry, right, is what constituents of the exoplanet's atmosphere are absorbing, and what are the absorption cross-sections? How does that lead to photoexcitation, to photodissociation, ionization? Well, it turns out that in broad strokes, because a lot of the atomic and molecular constituents of atmospheres have wavelength-dependent cross-sections that change broadly over the UV part of the spectrum, that this stellar far UV to near UV flux ratio tends to be a pretty good indicator of what type of chemical impacts you're going to get. And I'll show you an example of that in a minute. So what we're finding with building these is, and this is a paper that David Wilson, who's in the audience, just published this year. With the M dwarfs, we're finding this far UV to near UV ratio to be about 1. And for solar-type stars, it's more like 10 to the minus 2, maybe a few parts in 10 to the minus 3. And so what are the impacts of these different spectral energy distributions on the type of atmospheres you're going to find? This is a paper by Vicki Meadows, who's using our data here. And what Vicki's paper is showing is the orange curve is showing a transmission spectrum of the Earth-Sun system. And the purple curve is showing the same planet, but around the M-dwarf Proxima Centauri. Right? And you notice these two transit spectra are completely different. Primarily, you're seeing big bands of methane, which is driven by differences in the near UV irradiation of that planet's atmosphere. But you also see differences in ozone and O2. And there was a lot of work done about 10 years ago to investigate what the impacts this might have on potential false positive biomarkers, where the idea that you could produce O2 and O3 photochemically in the atmospheres of these planets without life. And so there was a lot of work done here. And this was really in the lead up to JWST, because we were going to get JWST on the sky. We were going to take transmission spectra of all of these planets, and we were going to understand, was there life on these planets? What was the photochemistry on these planets? But there ended up being a little bit of a problem with this plan, as Zach told you in his talk a few weeks ago. So JWST has a sample now of something like 15 of these planets, and initial JWST results are all consistent with no atmospheres at all. So maybe we were asking the question the wrong way a little bit. Maybe instead of saying, what are those atmospheres going to be like, maybe we should have asked, are those planets going to have atmospheres at all? And I'm going to say a little bit more about this going forward. But I just wanted to give you a flavor for the types of observations that JWST is making. Like, why am I saying this? So there's two primary types of observations. When they're transits, when the planet crosses in front of the star, and we take spectroscopy during that time. And then the secondary eclipse observations, where the planet is coming around behind the star, and you get a combination of the thermal and reflected light from the star, the planet's thermal emission and the reflected light from the star in that observation. And both sets of observations are essentially consistent with no atmospheres. In the transit observations, we see this as a flat line. You can run these different models and basically rule out dense, high mean molecular weight atmospheres. In the secondary eclipse observations, we see this as the reflected light, or the thermal emission, being consistent with a black body with no overlying atmosphere to re-radiate the heat. So we get something that is a very hot surface, and that would look something like this, which is basically the points are consistent with a black body curve. So I'm not going to go into this in detail because Zach gave a really nice presentation of this. I want to emphasize this work is not done. So the transmission spectra are featureless so far, but the precision with JWST is not really good enough to detect truly Earth-like nitrogen or dense CO2-rich atmospheres. And the constraints from secondary eclipse are getting better, but there's still an envelope where we can't quite constrain these things, and it is possible that around particularly cool or old stars that some of these may maintain atmospheres. But this has given rise to the Rocky Worlds program. This is the largest director's discretionary time program that's been allocated on JWST thus far. So this grew out of that strategic working group that I was telling you about. This is 500 hours of JWST time to make secondary eclipse observations of a group of 9 exoplanets that straddle this cosmic shoreline, which I'll describe in more detail in a second. And this has been something that we've been doing after that working group. There's the Science Advisory Committee that, for those of us who have a hard time saying no to things, we're asked to do after the working group to lay this out, how we're going to make these observations, what the right targets are. And so that's been something that we're doing now. So let me jump to where the stars come in this story. So we're not really talking about what are the atmospheres like anymore. We're really focusing on, do those planets have atmospheres now? And so that's really focused on a different part of the stellar spectral energy distribution. We're going to go to higher energies, into the extreme ultraviolet and into the X-rays, and also the effects of time variable things like coronal mass ejections, the stellar wind that drive atmospheric mass loss. And so the way this is being considered in a lot of this discussion, particularly the Rocky Worlds DDT program, but it's also become very popular in the field, is in the context of this cosmic shoreline plot. And really this is a simplified framework for understanding which planets can maintain an atmosphere. It's just sort of a simple energy balance equation where you have the stellar gravity, or the planet's gravity, characterized by the escape velocity on one axis, and the stellar energy input on the x-axis. And so the idea here is if you're on this side of the line, the atmospheres survive. If you're on that side of the line, the atmospheres probably don't survive. And so this y-axis is typically the time-integrated high-energy radiation that the planet has received over its entire life. So if we want to, so this is a radial velocity measurement, right, to get the escape velocity of the planet. But if we want to understand the y-axis of this plot, so we can start to place these planets on here, we're going to need the present-day XUV flux and then the history of that XUV flux, so we can integrate it back in time to understand the cumulative distribution. So we talk about XUV, but all photons are not created equal, so we have a lot of X-ray observatories, but it turns out that X-rays alone really are not telling the story for the influences on the planet's atmosphere. So I wanted to break this out in a little bit more granularity, and instead of talking about XUV, talk about X-ray and EUV separately. So if we compare the EUV and X-ray influences, the photoabsorption cross-sections that I was mentioning earlier are all orders of magnitude higher in the extreme ultraviolet. The EUV photons are absorbed higher up in the atmosphere, where they're able to dump their energy into heat. The X-rays tend to be absorbed deeper down, where they can cool via, where the atmosphere can cool via radiation. This is shown in this plot from a paper that Alison Youngblood and I and several collaborators published that shows this is the normalized photoelectron energy deposition. So essentially where it's bright, the photoelectrons are depositing a lot of energy. And somewhere around 120 kilometers is where you get the densities high enough that you get efficient atomic and molecular line cooling. So the X-rays are dumping their energy down here around 100 kilometers where they cool effectively and you don't put a lot of heat in the atmosphere. But here in the extreme UV, you're actually depositing your energy further up where it can go into driving work. So there are two factors that are sort of planetary atmosphere factors that drive the extreme ultraviolet to really dominate this process. And the third is that there are actually just more EUV photons from every type of star. And so when we talk about looking for the present day XUV radiation, really the most important part about answering this is the present day EUV radiation. So you might ask yourself then, well, what do we know about the present day EUV radiation from other stars? Well, I think it's best captured in this sort of seminal paper by Ribas et al., 2005, this Sun and Time paper. Many of you are probably familiar with it. This has looked at the evolution of solar-type stars in a couple of different wave bands. There is the extreme ultraviolet that we're talking about, 10 to 36 nanometers for this example. And those are the 4 solar-type stars that we have. One of them is the Sun. We have very good measurements of that. And there are also about 4 M-dwarf stars that are all very, very young M-dwarfs. And this makes up the entire sample, about 5 high-quality EUV spectra of other stars. And this is a pretty small number, right? Right, OK. Just write that. You can send my wife an email later. So why is this? Why do we have this small number of actual observations? Well, the interstellar medium is a large opacity source, right? We have a lot of atomic hydrogen and helium in the ISM, and those cross-sections also peak in the EUV. But probably the largest reason, which I will come back to, is that astronomy's never had a high-sensitivity EUV mission before. OK, so that's one thing. We need to know, we need to actually be able to measure these things. 2, we need to understand what the long-term evolution of this EUV flux is. So I'm showing a plot from a paper using scaling relations to estimate the EUV flux that we published this year, just for a very focused sample of solar analogs, where we were actually able to draw out the solar EUV evolution for the first time over this full range of very, very young stars right after they've, or actually just before they've joined the main sequence, all the way out to past 10 gigayears. And this, for those of you who are familiar with how stars evolve, or cool stars evolve, this follows the expected behavior of a magnetic activity saturation early on in the life, and then a magnetic spin down after that. So this is the history, at least to within the uncertainties of the scaling relations, the history for the Sun. But what if we put M-dwarfs on that same plot? They look like this. And you see a couple of different things. One, the turnoff for the M-dwarfs is much later. So the M-dwarfs are spending 10 or 20 times longer in this high-energy saturated regime. And then the spin down happens at a different rate and at a different level. So taken all together, normalized by the fact that the M-dwarf habitable zone is closer, the M-dwarf is dumping about 10 to 20 times more EUV radiation into their planetary atmospheres over time than the Sun-Earth system is. So we'll come and talk about that in a minute in the context of this, this cosmic shoreline. But so that was 1 and 2, and I wanted to just finish with number 3 here, any other factors that might increase or decrease the escape rate, right? Again, this is a gross oversimplification, but I wanted to capture the time variable terms. There's an important term in here that I'm not going to talk about, which is steady state stellar winds. You can ask me about them later. They're hard to measure. I will probably give you an answer that feels uncomfortable, but I'll be happy to say it. But I want to talk for a second about stellar particles in the form of coronal mass ejections and increases in the EUV from flares. So one of the things that we found is that while the flare rate for cool stars and M-dwarfs in particular goes down over time, when you observe them in the X-rays and the extreme UV, or the far UV, they maintain high flare rates essentially for infinity. We've observed very, very old M-dwarfs, older than 10 gigayears, that have 130-day rotation periods, very little sign of activity in their optical indicators, and they still flare in the X-rays and the far UV all the time. So this is a paper from one of Park Lloyd's papers. So one of the things we know from the sun is that these far UV flares are often associated with coronal mass ejections, right? These are from in situ measurements where you can actually measure the particles from the GOES satellites. We can't do that with CMEs, but we can build scaling relations for that. But it's important to actually have both of these because the CME and the stellar photon inputs drive essentially the whole range of relevant escape processes that we think operate in these exoplanetary environments. They probably operate with different efficiencies compared to what we have here on Earth, Mars, and Venus. But they're all important, and you really only have a handle on all of them if you have both the photons and some indication of the particles. So the next question is, what do we know about the CMEs on other stars? Again, it's actually really not very much. I would say there is no unambiguous detection of a coronal mass ejection on another star. I'll look at Utah. I saw Utah here. Maybe Utah would agree with me. There are a couple of suggestive observations, and I'm just going to show you one example from a paper that we published in Nature Astronomy last month of what we think is good kinematic evidence for coronal mass ejection on a young solar analog. This is an observation from Hubble, again, one of those muscles-related programs. This is the light curve, time on this axis and luminosity on this axis, and you see there's this pre-flare period, and then this big flare happens. And during that big flare, we see the 10 to the 5K gas show a big blue shift, like minus 500 kilometers a second, which we associate with an eruption related to the CME. And then a bit later, we see a cool filament absorption that's shown here in this cartoon, a cool filament absorption. And these things independently are consistent with observations of solar CMEs. Again, the scales are different, and there's still uncertainties. But we think we're starting to use kinematics to be able to have pretty good indications that these are happening on other stars and to be able to characterize their properties. I'll also mention that just last week, there was also another Nature Astronomy paper about a type 2 radio burst from a very, very young active M dwarf, which is another sign of a CME on the sun. Okay, so we would like to know more about that. But let me bring all of these bits and pieces back together to our cosmic shoreline and talk about the impacts for M dwarfs. Okay, so let's imagine that we're looking at this rocky-ish planet here orbiting a nearby red dwarf. So because we don't have the present-day EUV radiation, we have to rely on scaling relations or some other type of calculation, and there's a fair amount of uncertainty related to that. We talked about the higher effects from the longer evolutionary period in the EUV, so that's going to drive it up. And then, even for these old M stars, this is that actual M star with 2, we observed it for 40 kiloseconds, and 37 of those kiloseconds were totally dominated by X-ray flares. So you add another, look, it's spinning. And so that's how damaging it is to this atmosphere. So you add all of these things up, right? And it's maybe not a terrible surprise that we're not finding thick atmospheres on these rocky planets around M dwarfs. Okay, but you should take everything I said with a grain of salt, right? Very little of this is based on actual empirical measurements. So the question is, how do we resolve some of these uncertainties and drop these down so we can reliably place these objects on this cosmic shoreline? And so that's where this mission that we developed at CU a few years ago called ESCAPE comes in. This is a mission to do direct EUV and far UV spectroscopy of about 300 stars. Remember I told you the current sample size is like 5 or 6. And then do a deep dive observations on about 24 of these objects to observe CMEs directly using sun as a star techniques and characterize the EUV flare rates. So this was great. We had this idea even before this was hip to talk about. And we were one of the 2 missions that was selected in the Small Explorer round in 2020 for a Phase A study. And unfortunately, we came in 2nd place. And then we were really, really gung-ho to go do it again when NASA said they were going to have another opportunity in 2024. And then again this year. And then we were really ready to do it next year too, but now maybe it's going to happen in 2027. So my enthusiasm for this at the moment is a little bit lower than it would have been if I was giving this talk like a year ago, but bear with me. So how do we do this, right? We need to be if we're going to do factors of 100 times more stars than have done previously, right, we're going to need about a factor of 100 times the sensitivity. And so this is the escape sensitivity curve here in black. And so we're achieving factors of 50 to 100 greater than EUVE, which is the last mission to do this. And so we need new experimental techniques if we're going to do that. So, okay. So once you have a sample this size, you can actually start to develop the evolutionary history of stars as a function of mass and activity. So this is a sort of an estimate of what we would imagine sort of the complete escape data set would look like. So you have age here on the x-axis and measured EUV luminosity on this axis, and they're color-coded by spectral types. And so now if you want to know the history of M stars, right, you would just go in and you take the 60 M stars that you have in there, and you'd be able to, that are all of different ages, and understand the history of M stars, K stars, and understand what that means for the evolution of the planets. Similarly, we would observe CMEs. I'd call this is sort of maybe, some people would call this direct measurement, but you're not actually measuring the particles, so I guess we'll call it indirect. So on the sun, we observe CMEs through this coronal dimming technique, where when a CME happens, it blows the quiescent plasma out of the stellar atmosphere, and we actually see the quiescent extreme ultraviolet emission, or the extreme ultraviolet emission goes down as the material gets blown out. So we can see this in spatially resolved observations on the sun. We can also do this with the SDO-EVE instrument in a spatially unresolved way, so the sun is a star. And they have this characteristic light curve where you follow the dimming down. It's a couple of percent for large CMEs. And we can actually use this technique to not just measure the fact that a CME has happened, but we can also use it to measure its kinetic energy. So its mass and its velocity are encoded in this light curve. And that's also part of what ESCAPE will do. So, but we can't be deterred by the fact that NASA doesn't know what's going on. And so we proposed a precursor mission while we're waiting for ESCAPE called MANTIS. And MANTIS is a 16U CubeSat that was selected in 2023. And it is essentially baby ESCAPE. The idea was that we were going to do some precursor science and demonstrate most of the technology that we would actually need for ESCAPE. And so we won this, and excitingly, we have early career research scientists who have taken the lead role in this. So David and Brianna's not here, I don't think. But this is, so we're building this mission now, and we expect to launch it sometime in 2027. It also actually has more sensitivity than EUVE, but it's still about a factor of 25 or so less than ESCAPE. So we're not going to really do the entire science case, but as a scientific and technical demo, that's what we're up to now. And so we've got hardwares coming in right now. This is a first light image from the prototype telescope. We're doing this extreme ultraviolet grazing incidence telescope of a type that's never been built and flown before. So we're doing it in a baby version on MANTIS, and we're actually getting the hardware hopefully by the end of this year. Okay, so just after 4 o'clock, perfect. So let me summarize this first part of the talk. So I don't want to give the impression that the story is closed with JWST. There's a lot more work to do. This Rocky Worlds Director's Discretionary Program, I think, is going to really give us a good handle on the frequency of atmospheric survival on rocky planets around red dwarfs. But the initial observations suggest that things may be kind of grim for atmospheres on these terrestrial planets. So this kind of naturally leads to the question of, well, what star-planet systems are conducive to maintaining habitable conditions, right? We've done that for a long period of time now. And after we ask that question, we want to say, well, how do we actually find those planets? And so that's where the second 37% of the talk comes in, which is going to be about the answer to this question is the Habitable Worlds Observatory. And so what is the Habitable Worlds Observatory? This is NASA's next flagship mission. It was the top large mission recommendation in Astro 2020. It's the first mission that's specifically designed to search for signs of life on planets outside the solar system. And it's also, you can kind of think of it as a super Hubble Space Telescope, so it also does to about 100 times better everything that we're used to Hubble doing. There's a whole range of galactic astrophysics, essentially everything you can imagine, that I'm not going to talk about this today. That's kind of a different talk. And so I introduced the idea of transit spectroscopy and secondary eclipse observations. So these are sort of not exactly either. This is direct reflected light spectroscopy. So what's going to work for HabWorlds is there's going to be a starlight suppression system. On HabWorlds, we'll use a coronagraph. So the coronagraph will essentially put an occulting disk over the bright star and then be able to image the orbiting planetary system. This is a simulation with realistic instrument parameters over a span of about 10 years for the solar system placed at 10 parsecs away. And I'm not going to talk about the technical challenges of this today, but this is really the tall pole. This starlight suppression system is really the tall pole for this observatory coming into being, because the star-planet contrast is about a factor of 10 billion. So that means for every one planetary photon that comes into our system, there are 10 billion stellar photons that we have to effectively get rid of, or they swamp the signal. And so this is hard. And so this is where the really big investments in coronagraph technology and ultra-stable telescopes are being made right now. And if I've got time, I'll talk about that just for a minute at the end. So we're going to make movies of planetary systems. But that's not all, because that alone, just seeing the pale blue dot, doesn't really tell you that for sure that that's an Earth-like planet. So we have to go one step further than that. We have to identify where these rocky planets are, and we have to take spectra of their atmospheres. So there'll be a spectrometer that sits behind the coronagraph, and this is the type of observation that we're imagining. This is actually a simulation of that same system, or something very similar to that system. And so what are we looking for in the spectrum here? Well, we're looking for water, right? Water itself is not a biomarker, but our understanding of Earth-like life doesn't really have a good understanding of how you could form surface life without water, so we want to look for signs of habitable environments. We want to look for oxygen, because here on Earth, oxygen would not exist in any sort of serious abundance without a disequilibrium process like life. And then we want to look for things like methane and maybe SO2 and a few other things as an indicator both of more complex life, but also methane is probably the top biosignature from life before there was a lot of oxygen here in Earth's atmosphere. So you want to have broad wavelength coverage to do this. And it's not just broad wavelength coverage to search for modern Earth, right? This is that same spectrum essentially, but shown without error bars for modern Earth. But this is only, modern Earth with modern Earth's oxygen levels has only been about the last 10% of Earth's inhabited history. So if you want to roll back the clock and ask, could we find Earth 2 billion years ago? You actually start to look for different spectral features. Instead of O2, which is now very low in early oxygen environment, now the ozone bands in the near UV are no longer saturated and can become a very sensitive measure of the atmospheric oxygen abundance. So we need a broad wavelength coverage, not just to understand a wide range of potential biologic signatures, but also to understand how those evolve over time. So you need to have broad wavelength coverage, but you also need to have a fairly large telescope. So if you have a small telescope, as small as 4 meters, that's actually an enormous space telescope. But if you have a modestly enormous space telescope, like this 4-meter version, you're sensitive to about 8 candidate exo-Earths. Now, if we assume that the fraction of Earth-like planets around Sun-like stars is maybe about 20%, there's a pretty good error bar on that. But if it's maybe around 20%, there's a reasonable chance you don't find anything. And you don't really have a serious statistical constraint on what that means. And so really what you've done is motivated building a yet bigger telescope, and that angers people. So we're going to try not to do that. But if you go to a larger telescope, you can get to about 25 candidate Earths, assuming these numbers. And then with 25 exo-Earth candidates, right, and this is also, of course, what the decadal survey explicitly said must be done, you've got about a 95% chance that you will find an inhabited planet, with some assumptions on what eta sub Earth actually is. So taken together, for the purposes of this talk, right, this is HabWorlds. It is the future flagship observatory. It's coming to find those true Earth-Sun analogs. It's actually not very good for finding planets around red dwarfs, and do this whole range of astrophysics. And it'll probably look something like this. One of the things you'll notice, people say, well, why does it look different than JWST? It's got the barrel on it, so it doesn't get hit by micrometeorites like has happened to JWST, because it would be almost fatal for this system if something like that were to happen. OK, great. All right, so I wasn't sure how I was going to be doing on time, so I'm not really going to summarize now. I'm going to go to the backup slides, which were my aspirational backup slides. So I wanted to take just a few minutes in my last couple of minutes to talk about what's going on with Habitable. And so people have asked, like, is this a real mission? Is this going to be built? When is this going to be launched? How much is it going to be cost? What will it cost? Don't ask me the last one. And what's really happening? So I wanted to take a little bit of time, since this is actually a real mission now, to give you an update on that. So here's my simplified timeline. This is not NASA approved, but this is my version of this. So in November 2020, right, the decadal survey came out late because of COVID. In January of 2023, at the AAS, Mark Clampin announced that the NASA was moving ahead with a large optical UV IR telescope, and consistent with what the decadal survey said. By the end of October, there were these two science and technology teams that were formed. They were called the START and the TAG. And then science working groups had spun up by the beginning of 2024. I'm not going to talk in great detail about this process, but just to say that there were large groups of people studying different types of potential science cases, exoplanets, stars and galaxies, groups working on technology, groups were doing things that met here in the middle. And the one thing that was really exciting about this is how many people volunteered to get involved. So this is that first AAS meeting where the people who'd been appointed to the START and the TAG showed up. And every time we had a meeting after that, the number basically doubled. So we met a few months later, and the number doubled. And then we met a few months later, and the number doubled. And then we met that summer, and the number doubled. And ultimately, over 1,000 people contributed to developing the science cases for the Habitable Worlds Observatory. And now there's this sort of repository of about 75 science cases that are in there that the project office is working on now. So moving forward a little bit, in August of 2024, Congress actually required the establishment of a project office at NASA Goddard. So this actually means the mission is really real now, right? Hubble has a project office, JWST has a project office. Concepts do not have project offices. Because this happened, this meant that there were some legal reasons that meant that the START and TAG teams had to go away because of some NASA stuff. And so they formed a new, but much smaller, community and science instrument team in June of this year, and then a science interest group for the community after that. So, I'm part of the community science and instrument team. So what are our jobs? So we're in the process right now of identifying and quantifying these driving science cases from that large group of 75. Understanding what the requirements are for the instrument concepts, developing level 1 mission requirements, and also serving as sort of the ambassadors out to the larger community, which is in part why I wanted to put it in the talk today. There's also the community science interest groups, and so these are a group of people who are studying, or basically coming out of the existing program analysis group structure, a little too much NASA speak on this slide. The program analysis group structure for exoplanets, for cosmic origins, and for physics of the cosmos. And this is an opportunity, these are the individual working groups that are developing science questions and supporting analysis that are helping the project office. I'll put this QR code back up, but these are open to anybody, so if you're interested in getting involved, I really encourage you to snap that. All right, looking beyond that, so this is where we are here at the end of 2025. Probably, now the government is back open, somewhere in the first half of 2026, there'll be instrument studies that happen. There'll be a design reference mission and level 1 requirements that happen in 2027 and 2028. The decadal survey said before the next decadal, you need to go through a mission confirmation review to make sure the mission is in a mature enough state to proceed. So that's not really scheduled, but probably will happen sometime in 2029. That'll lead into phase A and a launch sometime, hopefully just before 2040, but that's uncertain at this point. So that's what's going on. It's really happening. There are lots and lots of people involved. There's lots of opportunities for students and faculty and scientists to get involved. And it also sort of brings home the last bit of the talk, since I have an extra few minutes, that I want to talk about where our group at CU is engaged in this process is on the instrument side, as Zach mentioned in his very nice introduction. So one of the things that we've been doing for over a decade now is developing specific hardware components and design concepts for essentially this mission. We didn't know to call it HWO at the time. It was LUVOIR for a while. Before that, it was At Last. But we've known for a long time that there's going to be a need to develop something that is sort of a super Hubble Space Telescope. And so that's where some of the work for the technology advancement for HabWorlds is happening now. So there'll be things like, and I'm not giving a complete example here, but things like telescope design and optical coatings for telescopes, the ultra-stable mirrors that we need to do this high-precision coronagraphy to keep the mirrors stable so you can measure these 1 part in 10 to the 10 signals. Some of these things are being launched and tested on suborbital flights, which I'll talk about in a second, and then planning now for servicing, which Dr. Grunsfeld talked about in his colloquium a couple of weeks ago. So the lesson from Hubble is that the reason why Hubble was so amazing for 35 years is because we could service it. And so the plan is to be able to service HWO2. So let me just show just a couple of examples of some of the things that we've been doing here over the last couple of years. So through our sounding rocket programs, and this is in particular the CHESS and the Sistine payloads, we've been developing advanced diffraction grading technology. So this is a diffraction grading efficiency. This is going to be technical for a second or two. This is the diffraction efficiency of a shell grading as a function of wavelength. The state of the art here is flying on Hubble right now. It's about 25% with lots of nasty scatter. We have already improved this by about a factor of 2.5, right? This is a lot. There aren't very many ways that you can multiply the sensitivity of your instrument by 2.5 without making a much, much larger telescope, but improved diffraction gratings are one of them. So this is something that grew out of one of our sounding rocket programs, but grew into a collaboration with CU alum, Randy McIntaffer, who was a Webb student. And Brian has taken on the lead role here at CU. And this is just an example of before with our relatively crummy diffraction gratings, right? We would spread light over. These are multiple orders, but now with improved diffraction gratings, we're putting all of the light in the order you want. That's essentially the same thing as that plot on the top is saying that your peak order efficiency is going way up, and you can also see that the scatter is going down. As part of our current ongoing work, we're also developing filters for HabWorlds. This is related to Emily Farr's NESSF that she's doing right now. So we're building these. We're testing them on sounding rockets. Next year, we're going to, oh, that's right. I forgot I put that in there. Right, I can't show sounding rocket things without showing a sounding rocket launch. It does that for a while. Next year, we're going to launch the Sprite small sat that Brian is the PI of, and Maddie Bowen, who's here, is the lead graduate student. So Sprite's been instrumental, no pun intended, for testing the advanced optical coatings we hope to fly on HabWorlds, including on optics and diffraction gratings. So these are going to fly and be flight demonstrated probably next spring. The science of Sprite is a little bit different. Sprite's actually designed to go out and measure ionizing radiation leaking from nearby galaxies and build spectral mapping of nearby galaxies and supernova remnants. If you're interested in that, you can talk to Maddie after the talk. But that's coming after that. And then finally, the last thing that I want to say is that there's a recognition that when you're building something really big, that these are multi-generational projects now, and the people who are leading these projects today are probably not going to be the people who are building it 15 years from now and who are doing science, let's say 10 years from now, you didn't hear me say 15, 10 years from now, and who are doing science with it 15 or 17 or 18 years from now. So we really need to get students involved in all of these processes, in the science side of what we've talked about today and in the instrument side of what we've talked about today, because these are the people who are going to actually do the work with HabWorlds. And so that's one of the things that we've worked on a lot in our group over the past 15 years or so. We're bringing early career people into the projects. These are all the graduate students that have worked on our suborbital projects for maybe, this is only about the last 8 years. There are people from before that. We would get new early career folks in as PIs, bring in scientists and engineers, and give them the opportunity to fail on these projects while they learn a whole lot, so then they can go on and do these things successfully on large missions in the future. All right, so now I'm really going to stay up, wrap up here. So I think here are the things that we talked about today that I would like you to take home. So there's more to habitability than just being in the habitable zone, right? So there are lots of those rocky planets around red dwarfs that are in the habitable zone, but may not have habitable atmospheres. Right, okay, back to my hiking analogy again. So the host stars differ widely by mass and age, and this leads to different exoplanet outcomes. Right? That's kind of the low-level way of saying it. Atmospheric retention, there was a really nice meeting in Baltimore 2 weeks ago that talked about all the physics of atmospheric escape and replenishment. Some of the major stellar drivers are really unconstrained by observations today, but this is something that I think we can actually address with small missions. And we may be seeing the effects of this right now with the M-dwarf planets that we're observing with JWST. And then ultimately, right, we want to find Earth 2.0. We want to find a planet that has habitable conditions, the signs of life that we understand. And I really think that this is leading us to the Habitable Worlds Observatory, which hopefully, when I can come give my pre-retirement talk, I will tell you how awesome it's going. So thanks again, and I'm happy to take any questions.
Questions?
Great talk, Kevin. Thank you. So I'm going to ask you to predict the future, so I apologize right off the bat. So hypothetically, let's imagine we live in a world that has potentially chaotic budgets. How likely do you think it is that the Habitable Worlds Observatory will actually see completion?
Yeah, so I mean, let me answer that in 100% confidence. Let me answer that in maybe 2 ways. One, when things were really scary with the budgets in May, June of this year, NASA zeroed everything in astrophysics in the future out, zeros. And right, we saw that in lots of different science divisions. The only thing that happened in the future was we launched Roman, which is already built, and HabWorlds keeps going. So, and if you look at what the House and Senate appropriations bills have put together, they basically put HabWorlds on track. So yes, can we really see what's going to happen in the future? No. But this is, NASA works on the #1 decadal recommendation, and this is that. So.
Hi, Kevin. So what is the #1 question you want to see answered with Habitable Worlds?
Oh, I think the #1 question that I would like to see is, I feel optimistic that we will find planets that have signs of habitability. I think the question of how we define that is still a work in progress, and I think there are probably going to be a lot of debates about that when the data come in. But the thing that I think would actually be most interesting is if we build an ambitious telescope and we have a couple dozen of these, and we can understand how the atmospheres of the planets change with the stellar conditions, right? So let's imagine we're talking about K-dwarfs, right? Like, what do planets around K-dwarfs look like? And can we really understand them as comparative planetology, where we put Earth or the Earth-Sun system is just one point in a much larger plot, where we actually have enough information to see things on different axes. I think that's what I would really like to see come out.
Mike?
Thanks for the great talk. When we're talking about habitable worlds, one of the cruxes of the mission is to be able to block out the stellar light. But that light from the star is one of the main components that determines the habitability of the planets that are orbiting them. So what are Habitable World's capabilities when it comes to characterizing the stellar conditions?
Amazing. Yes. So Habitable Worlds, will have this coronagraph to find and characterize the planets. It will have an imaging camera because you can't build a large telescope without taking amazing pictures. And it'll have probably 2 ultraviolet spectrometers. And so that ultraviolet spectrometer will essentially do all of that host star characterization, except for the EUV part. That part we will not be able to do. It actually requires a telescope that's really specified to do that, and that would not be a good fit for Habitable World. So, but that's okay, because you don't need a multi-billion-dollar mission to do that. You just need something that is tailored to that specific science question, which I think we can do in this small Explorer type package.
Thank you.
Thank you for the interesting talk. I have another question for Habitable World, and I think, in my understanding, there are several instruments. First time in first light instrument, and some other additional instrument. But how many will be selected, and also how is the current selection process?
Right. So the selection process hasn't started. So there are instrument concepts that are being led by NASA, and then probably in about 6 months there will be an openly competed instrument study call that will be for academia and industry outside of NASA. And right now in the current designs there are 5 instruments, or 5 instrument bays. So you can imagine that there is the coronagraph, the imager, 1 main UV spectrograph, and so there are probably 2 things that we really haven't defined yet. And probably it's imaging spectroscopy in the UV and maybe polarimetry would be my guess. But those are probably going to be a combination of US-led and internationally contributed instruments. And I think that process right there is a ton of international interest in developing instruments for Habitable Worlds and being part of the science.
You said not to ask you about stellar winds, right?
Yeah, don't ask me that. Yeah.
This is just a quick question. So you mentioned the Habitable Worlds Observatory is going to be able to detect planets orbiting the stars.
Mm-hmm.
But my question is, how big would that have to be? Because there is a specific collecting area for detecting all the photons that.
Right, so the size of the telescope is probably going to be somewhere between 7 and 8 meters. It looks like that is the required size. So that's a little bit bigger than JWST, but not dramatically so. And it will probably be a segmented telescope similar to JWST. The exact architecture they're still working on. There are a couple different ideas. But then once the photons are all collected in the system, then that's where the starlight suppression happens through a series of different masks and controllable mirrors that basically change the shape of the mirror to isolate the part of the where the planetary photons come in, and we call that nulling. They null that out, and then you can actually get a clear picture of the star. So the device that actually detects the planets after the light has come into the telescope the actual masks are pretty small, maybe the size of my hand. Does that answer your question?
Yeah.
Okay.
I was just concerned about to get a better definition of any planetary body, you need a very big collecting area, so all the photons
Yes.
your sensor can get.
So just to give you to put a number on that, right, we think about stars in terms of magnitudes, right? Our eye is sensitive to a 5th or 6th magnitude stars, and remember this is the weird astronomer thing. So as the number gets bigger, they're fainter. So the very faintest stars that we're observing with HST are around 30th magnitude, maybe 31st magnitude, and Earth-like planet at 10 parsecs is 33rd magnitude, so you really need a big telescope to be able to do this. This is why with that 4-meter version, you just don't see very many planets, because you just you don't go deep enough in volume to see it.
We've come up on 4:30, so let's thank our speaker again. If you do have other questions, you're welcome to come down and talk to Kevin.
Thank you, Andrew.
Spectacular.